How much am I?
Oh, you don't want to know.
Yeah.
Hey.
I believe 28. That's what everyone else did. Any questions before you get started? Any homeworks that I'm missing? Homework 2. I just passed every homework back that I have. So if you didn't get your homework back, it means I didn't get it. Okay. All right. More coffee? So we were talking about what? I don't remember. I don't have any notes on it.
Ampere's law.
Ampere's law with respect to H. And what the hell is this H thing? Because I didn't tell you, right? But what is H?
Is this the magnetic field caused by the free charge?
Magnetic field caused by the free charge? Okay. We have almost all the right words. We're missing one type of word. Current, right? Magnetic fields are caused by currents. Okay. And actually, H doesn't really have a name. So everyone's reading the book, right? And we all know that in the footnote, right? Footnote 17 or 7 or something on page, let's look for where it is. On page 282, he says this is a source of contention in the field. And we'll talk about why, generally speaking, people will have a problem, right? Some people call H the magnetic field, and some people call H the auxiliary field. I don't care. We're going to call it H. Because when it comes to light, we won't use H. But when it comes to anything you've ever done in a laboratory, you've never measured B. You've only measured H. And we'll show that today. Okay? Okay. So just to recap very, very briefly, we had something like Ampere's law. That's what I heard people say. And how does that work? Closed integral, this thing H. Yes, very good. And that's what? I. Very good. And what kind of I? Free. Enclosed. Very good. Oops, that's not an N. Closed. Okay. And this led to something like, if I'm thinking about a line like that, then I get some geometry, which is like this. Oh, this is not really working out well, but promises that'll get better. Okay, and this was analogous, right? So this had an analogy. To, if I do the same type of B dot DL, We've seen this before. B is just mu naught I over 2 pi s. Okay. And now for everyone who's already done the homework 428, I hope. Right? And you've turned that in, you found that there was this fun game that we played relating D and E in order to understand the potentials, integrate those potentials. You notice the similarities here. So generally speaking, we saw, oh, these are sort of the same. There's one minor difference. What minor differences here? The mu naught, yeah. And we saw that similarly with the D and the E, right? There was a little difference, and the difference there was
The epsilon.
epsilon, right? Okay. So we're drawing some similarities here. So we said something along the lines of B was mu naught. Oh God. H minus M. So this thing that we call H is modified by the magnetic polarizability and the magnetic field. We're going to see exactly how that works today, because there's these different types of magnetism where there isn't different types of electricity, right? Okay. Let's talk about that really briefly. Here's the types of magnetism again. They are just the main two, not the ferro. Dia. Okay. Diamagnetism has the magnetic susceptibility less than 0. What does that mean? Well, that just means that the magnetic dipole moment is anti-parallel to the B field. Okay? So it'll actually oppose the effects of the B field. Whereas paramagnetism greater than 0. Very good. Good guess. And so then what would that mean for the relationship between the magnetic polarizability and the B field? Parallel. Oh, interesting. Huh. It's almost like these little words in the front mean something, right? That they're not just thrown on for a lack of convenience. Para meaning, I didn't spell that right. And dia meaning opposed. I've also didn't spell that right. I cannot spell. That's not my forte. That's why I type things. Okay? All right. So this one we claim is parallel. Very good. This type of magnetism enhances the field. So the bound current, the current that's created from the magnetically polarizable material, is in the same direction as the free current. Okay, enhancing the field overall. That's different from the polarization, right? So even though we wrote this up here, we said that the total magnetic field, okay, is equal to H minus M, but M might have a weird minus sign. Okay, you can go either way. And because materials can be diamagnetic and paramagnetic, because they're different causes, right? Different materials will respond in different ways. Okay. So everything has a little bit of diamagnetism, because everything has electrons. And diamagnetism comes from? Yes, very good. Okay, good. So there's two things that electrons can do. Spin and orbit. Good. Spin and orbit. Okay. So here, yeah, there's very few guesses what electrons do. They have their charge and they move around. There's two different ways that they move around. Okay. So this one here is due to the orbit. And this one here is due to the spin. Okay, and the way that we would write this, we love quantum mechanics, right? Now that you're all 4 weeks into it, you're experts. Not experts yet? Almost 4 weeks in. Okay. All right. So you've heard of quantum numbers, right? Okay. You love them now? Because they're quantized 1, 2, 3, 4, 5. Okay. Well, the magnetic dipole moment for an electron essentially looks like this. Oh shit. Not like that. Okay. And this very cleverly is the contribution from the spin, and this is the contribution from the angular momentum from the orbit itself. Okay. Okay. Is spin a real quantity? Do electrons really spin? Raise your hand for yes. Raise your hand for no. Raise your hand what? Okay. Let me ask this a different way. What is the radius of an electron? 0. So how can something with 0 radius spin? Good, but no. No. So spin is a construct. Spin is an idea, but it behaves very much like the object is really spinning. So we can't think of it in the same way that we think about the word spin. When I think about spin, I think about this, right? I think about real rotation. But these things don't have size. So how could they be spinning, right? Moreover, it's an inherent quantity. I can take this pen and I can have it like that, but I can also have it in any of these states, right? Those are all perfectly acceptable pen states. For an electron, that's not true. You can spin up, you can spin down. It's an on-off button, right? So you can either have on, both up, and then their spins add, and this is non-zero, or they're not aligned, and therefore they cancel, the spins cancel, and this does not contribute. Okay, so in this case then, spin here is coming in the paramagnetism. If you have these electrons that are contributing their spin, you get paramagnetism. Make sense? Okay. Okay, so we have 2 different examples here. We can either do, I kind of don't want to do this one, but you might like it. Okay. We want to do, no, I don't want to say. Okay, let's just do this one first, and then we'll work backwards. Okay, so let's say we have a long copper rod with a current along it. You like copper rods? Okay. Copper is diamagnetic or no? Good. Which means that the dipoles line up opposite to B, right? They show down here. Diamagnetic, paramagnetic. Okay. So I'm going to have I going upwards. I'm going to put a little Amperean loop in here. And I would really like to understand in this material, this diamagnetic material, what B is.
Can we start with the Ampere's law? Or with the one with
Perhaps, yeah, that might be why I wrote it.
Probably.
I have a little Amperian loop here. That could be the hint. Right? Let's take 3 minutes, set up the problem for yourself, and then turn to your neighbor and see how far you can get. Because I'll tell you it's only 4 lines, 5 lines. We're set at that. It's okay. It's a straightforward. We're doing in-class example. And then we'll do it together. A lot of fun. It's nice. They're probably doing fluids. Unlikely, actually. You work first. Okay. For the people who are done right now, did you ask a friend you're 100% ready to explain it?
Which was 3 minutes.
I said like 3 minutes. Yeah, it's been 3 minutes.
I do have a question.
Beautiful watch.
What do you guys do?
I have
Yeah. You might have to throw an eraser design. Yeah.
So, and then
I think it's a keep more on this side.
oh, that's true.
I
So it's like all these like that.
Does it
Before I use like
there is a
well, like HWS, they also like for lines. So it's like, oh yeah, this one. Really, that.
I don't think
Like,
yeah. What?
This one?
Okay.
It is.
Yeah, like,
So it's like how the big M is the little M, which is the magnetic
about their
over the entire one outside.
This copper
So that's what I.
rod, if the current's going through it, usually but to release it, the magnetic dipole moment, that's where I'm like, still trying to think about it. And so the big M, that also influences the magnetic and H in this relationship, you have I, which is your current, over S. You could say we have S, where like we're looking at the interior of what's happening on the outside. So when S is smaller than that's like where you could look at, investigate to see if there is an H. And then on the outside, investigate and see if there is also an H. But I'm getting caught up in the end part.
Sorry.
Yeah. Like, yeah.
Well, it has some.
Yeah. Could we say that it behaves yeah, or could we just be like, oh, this is what you should be expecting?
We ready? And have their arguments about it? It's about how you do it. Yeah. Your head is the lowest, so therefore, whoever's eyes I can see the worst, that's who I'm gonna ask. I'll actually reads up next. Still.
Oh yeah, the crazy.
Uh-huh.
You know H minus M is that thing?
Okay, she started here. White.
Because we were talking about H, so I thought I should not just do E equals that, because maybe it's too simple now.
Right. So thinking about how we would do this problem, right? So we break down all the steps, right? So it's not like we got handed this down by, you know, holy source. So we're thinking, how would we approach this if we were on our own? And I told you this is a diamagnetic material, so you think in your head H, right? And then I asked you for B, so now you want to connect the two. So I get that, comes in, right? Okay, what else?
I just used the equation you wrote for H instead of doing the integral, because I thought it might be the same.
Yeah, that's pretty reasonable, right? I said thin wire. This looks like a wire, so that's okay, right? Is this true everywhere?
Thin wire? Oh, I don't know. Inside?
Yeah, very good. So is it true inside or outside, and how would you do the difference?
I am.
Okay.
Well,
So I drew a loop inside, and then after when people were talking, I drew another one outside.
I write one.
You're right for one, but which?
Now,
The inside.
Raise your hand for inside. Raise your hand for outside.
No, people.
for that.
All right, why don't you turn to a friend and tell them which one? Only if you have opposing views.
What do you, oh, okay. All right.
Would be out.
I did the outside, and it's just like, okay, the magnetic dipole moment into the inside of the wire, while the outside is just a magnetic
What would it be inside or outside?
Yeah. Yeah. That's what I'm afraid.
Yeah.
Okay. Which means these white might be 0. But I don't think that wrong.
So it's like.
Well, I mean, it has to.
Okay, we ready?
So like any man goes.
All right, raise your hand for inside.
For H, right?
For H.
Okay.
Raise your hand for outside. All right, let's do it then.
Let's find out.
Clear that this is not, I mean, there's a little bit of a confusion here. So how does this one work, right? We want H. What am I asking for? I'm going to create some surface integral H ds, and I'm using this loop here, and that's going to be the I enclosed, right? Okay, but I have to be a little careful here, because if I'm inside, then the I enclosed is a fraction of the total I, right? And we did this recently. We showed that the area goes as pi r squared. So this piece, when I'm inside, is going to be like I pi over pi r squared, right? Those will cancel fine. And this piece here is H times 2 pi s, correct? Okay. So what's H inside?
It's 1 over 2 pi.
Yeah, that's an S, just one S.
Oh, which direction? Did you see that from the picture? Yeah, we're using our right hand rule. We're sticking I up, and this is going in the phi direction, right?
Yeah.
Okay. So this one's inside. Is that what we have? Oh. So by definition, that has to be outside, right? Let's just double check it. Okay, so outside, what does it look like? So this thing here is just all of it now, right? All right, good. Okay, so this piece here is.
Yeah.
Yep.
And that's.
Yeah.
Is that the same? Okay, was that hard? No. So this is something we need to know how to do. We don't know how to use Ampere's law. If we don't know how to use Gauss's law, we won't be able to do anything, right? And the way we get better at it is doing it over and over and over and over and over. The geometries aren't that interesting, right? They're wires. They're boring as hell. They're circles. Sometimes they're a wire within a wire. Boring. Or a circle within a circle. That's just a wire, but it's circular, right? Do you see what I'm saying? So we just need to work on getting these into our understanding about how we do these types of problems. You want B, Ampere's law. You want E, Gauss's law.
Yeah.
Very good, right? Find the charge enclosed. Find the current enclosed, right? Okay. You may be thinking to yourself, well, Matteo, you're a liar. This is H, and you asked for B, right? And there was a nice little discussion here about what is M. So outside, let's ask this question first. Okay.
Outside, ask what M is.
Yeah, what's M outside?
I want to say 0.
Why 0?
Because
There's no
that
material left.
ability in the material.
Exactly. You're not in a material. You're outside the material. Good. So here M equals 0, comma, outside the material.
So that is B outside.
So this will be B outside. Well, kind of.
Well,
there's a relationship,
view
right?
will, yeah, or the view. Yeah.
Okay.
All right.
What about inside? There's an M, and I haven't taught you how to do M yet. Okay, so it's a trick. All right. So instead, you have something like B here is mu naught I over 2 pi r squared s plus something you don't know how to do. Okay. Is that fair? No, it's not fair. Okay, good. All right.
Wait, not on the outside.
Just
It's the,
it was in my notes, but that doesn't mean that it is. Let's do that. All right. Here, the one that is outside, this one is straightforward. Yeah, or mu naught H. That's funny. What does that look like? Oh, what the heck? Okay. That's amazing, right? No, it's not. It's just normal. Okay, no one's impressed. This is just EM2. No one even cares, right? So experimentally, the reason that we were talking about H, and for the folks who came in late, what is the definition of H?
You didn't define it.
You didn't come in late. You were here first.
Oh.
What is H? What's it mean?
it seems like it's a component of the magnetic field. It's like it's an amorphous thing right now.
Okay, so this is why we read the book too, in addition, and we'll find that H doesn't have a name, right? H is contentious because H is the only thing we measure. We never measure B, only measure H. So some people want to call H the magnetic field, and they want to call B the magnetic flux divergence. I don't want to do either of those things. I'm going to call B the magnetic field because when we talk about plasmas, when we talk about light, we're going to use B and we're not going to have H's. But in a laboratory where many of you may work, you are only ever measuring H because H is the result of it going through material, right? Okay. Okay. Did I delete this? Yeah. Maybe we'll delete this example here. We might do this other example afterwards where we look at surface amount charges, but we don't have time for it. Let's scrap it. Questions before we continue? When we're thinking about bound currents, you have to be careful. Okay? Just like we were thinking about these polarized materials, and inside of them, the atoms and molecules can change. They can change their orientation. The same thing is true of bound currents. Right? So we might have something that says del cross B. Okay, what does that mean again? B, what does that mean? That's the right hand movement, correct? This of B. Right?
Very similar to vorticity.
Yes, very similar to vorticity. So how much spinny up view is the B, right? Okay. And we said that that was something like this, no? Mu naught J. Okay. This is saying that the reason that we have magnetic fields is due to currents. Okay. This leads to Ampere's law, right? We use Stokes' theorem to rewrite this. We say something along the lines of B dot PL is equal to mu naught I enclosed. Okay? That's Ampere's law. Okay. Well, let's do the same thing here. What would that be?
That which out the mu naught.
Just J. Yeah.
Yeah. Okay.
Right? And so sometimes we do this. We do J free. Okay? And that leads to our Ampere's law for H. H dot PL is equal to I F. Okay. And then we said something, oh, maybe I just wrote this wrong here. Okay, it's inconsistent in my notes. Let's do this. Okay. I'm gonna write that again. We're gonna write here that B is related to mu naught H plus M and not the clothing store. So mu naught H is not equivalent to B. We saw that in the case where we're outside and we're looking in, we're thinking of them as the same thing. But inside of the material, we found that we were disturbed by this M thing that I had yet to really explain how you derive, right? Okay, so in practice, we can write M. Let's rearrange this. H is equal to 1 over mu naught B minus M. Okay, just moved it over. Okay, what's del dot H? Well, del dot H is 1 over mu naught del dot B minus del dot M. What's del dot B? That 0, correct. All right, and what is that condition? Divergence. Yeah, how do we just know that? I mean, we know that it's Maxwell's law, but what does it mean intuitively?
Oh, magnetic monopole, I think.
No magnetic monopoles. Okay, this is the condition. No magnetic monopole. And you say, well, what the fuck is a monopole? Charge. There's no magnetic charge carrier. Okay, there's only electric charge carriers. Okay. So then this essentially means that del dot H is equal to minus M del dot M. Okay. So I could say something along the lines of JF equals 0 does not imply that H equals 0. Okay. Just like rho of F equals 0 is not equivalent to E being 0. Not. Okay. Here, look at an example that seemed unreasonable. Let's see which one of these do I want to do. Okay. All right. Let's take a coaxial cable. The picture up here. We're gonna have 4 regions. This will be regional 1. This is radius A. This is region 2. Radius B. Sorry, not 4, 3. And this is region 3. Okay. On the exterior, on this piece here, I have I going in that direction. And on this piece going backwards, I have I going in the opposite direction. Is that reasonable? The inner is solid here. The outer simply has a surface current. And the inside has some magnetic permeability. Okay. Let's find H in all three regions.
Is the X thingy, is it positive or negative?
What do you, this thing?
Yeah.
The permeability?
Yeah.
Doesn't matter right now. You can think of it in the context of the example that we just did, which was also a wire.
So it's diametric.
The diametric materials in here, or diamagnetic materials in here. This stuff has diamagnetic. This is just current. It's just plain old current. Okay, how we doing? You want to turn to your friend and ask them if they did?
Oh, okay.
That area, you wanted, we were probably. So that's what I heard.
That might be, yeah. I was looking at one.
One.
One was tough, yeah. Maybe I should just look at 3 first, because that makes a little more sense.
Like getting one.
Oh,
Yeah. Really much is all the here's like this.
I think this would be a little bit.
Yeah, we didn't really care about the length. Yeah. So it's like, oh, yeah, it's just on game, but I kind of. And I did that. I was gonna hear, so still kind of want to make the actually, why did you PHYS? We're now.
That's why.
Oh, because
That's kind of what I was thinking.
What did you do?
Yeah, maybe that's just.
Yeah. Oh, yeah.
Yeah,
How is
that is
What's that?
Is it?
I feel like they could have canceled.
Yeah,
I guess if I is the
That's kind of.
Okay, folks, how we doing?
Okay.
What's H3?
I started.
Yeah, that's the hardest one.
That's the easiest one.
That was actually the easiest.
Why is it 0? It's I minus I. Remember, what's the point of writing this stuff on the board and saying, let's find H? What is H? What do you think when I say find H?
Find it.
Find it. How? What's the tool we use?
The second one.
Ampere's law.
Yeah.
Right? You might get into something like this and start finding all this jibbity jabbity with the B's and the M's and don't. If I give you I, if I show you where the currents are, the first thing you think to yourself, okay, let's find out how much current is enclosed. Now, if I didn't give you I, and I gave you M or something else, you're right, it'd be much more complicated. But let's not overthink this. This is an in-class problem. Okay, so H3 is what's H2?
I thought H2 would be 0.
Why?
Because I assumed that it was experiencing opposing magnetic field as well.
What do you mean opposing magnetic?
So the current that's going through, I guess, section 1, it's producing a magnetic field that's like, I guess, in a negative phi direction, and then because of what's on the surface of, I guess, 3, it's producing a magnetic field in the positive phi direction.
So I follow your reasoning.
Yeah.
So here you have something, right? This like shell, and it's going in this direction, and you're thinking, well, the magnetic field is permeating into it. Is that true?
Oh, it's out of it. Yeah, okay, so there's still, okay,
I was just gonna say, like, if you were doing it, an invariant loop in, like, in zone 2, then it would only encompass the first eye.
Right. So if we are to believe Ampere, pretty good, because it's been around for a while. No one's come up with a better law. Okay, this current doesn't matter in 2. So in 2, it just looks like a current going that way. Do we know what that looks like?
it looks like it was independent.
Yeah, but what's the letters?
That is
I over 2 pi down here or up here? On the bottom. Very good.
Yeah.
Good. And which direction? Very good. All right, what about this one?
Over 2 pi a squared plus x. A squared. Hence.
Is that correct?
Oh, negative.
Well, which one's negative? We have to choose one of them. Okay. All right, it doesn't really matter. We can do that. Okay, good. Was that hard? No. Did we overcomplicate it in our heads?
Yes.
Yes. So let's make sure we don't fall into that trap. Because if we were to have a test, say week after next, we can talk about at the end of this. You know, you'd want to make sure that you didn't get yourself in a little hole, right? Okay. So let's think about the way that this physically connects, because this is a real thing that happens in nature. And not nature, you don't find these in the ground, but you know, we make them. And so you have these 3 regions, and they're supposed to be smooth, right? That they can't have some weird discontinuity. Okay. We can write surface currents in a few seconds. Can you find the surface current here? The free surface
Current over surface.
Yeah, what would that mean?
Would we be using B for
Yeah, 2 pi b.
Yeah.
Okay, good. All right. So let's look really briefly at what let me write this properly. Here is h is a function of radius or s. Okay. So this goes in this section before you get to A, it goes up linearly, and then it goes down, and it doesn't go to 0 if you get to the surface, and then it goes 0. Scary, right? That doesn't seem reasonable. So what's B then?
If we
Let's do the hardest one. B3?
Yeah.
Good. Okay, very good. All right, that one we're still consistent on. If we were thinking about it in this context, right, and there's this relationship with B and mu naught, and I said this thing about mu and mu naught, which of these 3 regions does this apply to?
Only 2.
To region 2, right? So if I were to say something like mu1, mu in region 1, mu in region 3, and mu in region 2, which of these are the same? 1 and 3, right? These have to be the same, and they're also equal to 0. You're on a roll, almost there. You were on a roll. You're thinking this would be 0, right? But I'm not asking for this, I'm asking for this. Mu naught, right? This would be the permeability of the I don't know what it's called. I'll look it up. But it's the mu of free, right? Okay. It's a mu of free. And this one here would be the one that is this piece, right? So this piece is 1 plus whatever the diamagnetization of this material is. times mu naught. Okay. So we can generally, right? We want to ignore this little m here. We can say something like B is equal to mu. Oh shit. That's wrong. It looks so similar. That. Okay. Notice that this is mu, not mu naught. Okay, so I'm incorporating that diamagnetization into this term. Okay, so then how would I write B1?
Would it just be times mu naught?
Bada bing, bada boom, right? What about B2?
That's when they need to find the
The what? That's when you need M?
Yeah.
What?
I just gave you this.
What?
I just gave you this.
Why can you
I just-
do this?
I will get to that in a few seconds.
No,
I don't want to do it yet. I'm going to show you something and you're like, ooh, ah. Or maybe we'll see. Well, we'll find out. Okay. So this one here. What?
Just multiply by mu.
By mu, correct. Okay, mu I over 2 pi. All right. Okay, so, sorry about that. So this means that if I look at this field here, it's still going like S. I'm not going to write it a second time. You see it here. You get it. All right. Now you see this discontinuity, right? Going from here, it's dropping. So we need to connect that. And this discontinuity actually indicates to us something important about the physical object we're looking at. It's saying that there are magnetized surface currents from the fact that there is a polarized material inside. What? What are you talking about there? Okay, let's look at this. We kind of wrote that already here. We have M1, we have M3. Let's write it in terms of psi. Okay. What's that one? Zero, very good. What's this one? So in the places where there isn't a diamagnetic material, then good. the magnetic susceptibility is 0. Good. And we said this one here is this one. We can kind of clean up some of that literature there. That means that the magnetic moment in 1 is 0. And it's also in 3, right? Okay. Now this is the tricky one. So in region 2, what would it be?
You just said
What?
Didn't you just say M1 and M3 that you not?
M3 and M1?
Yeah, right there. Isn't that the same as these M's?
No. Mu is different.
No, this is psi. This is the permeability.
I agree with that.
No, you talk about the.
Yeah, and
This is M, the magnetic dipole moment, and this is mu.
It's like the free
Hold on.
those are green days.
Hold on, sorry. I'm so sorry.
Here.
Is that better?
you should just write MU. No, I'm kidding, I'm kidding. No.
Kids these days, so demanding. My chicken scratch that I had to learn when I was walking to school each way 6 miles in traffic. Oh my god. Well, because we don't have snow in California, so I walked in traffic. You never heard of that? Yeah, 6 miles both way. All right.
Anyway.
All right. So here we have this magnetic polarizability. That's the thing that we're folding into this discussion. Okay. And my question is, how the heck would we find this?
Of that earlier relationship you wrote on the board. Looks like it had angular momentum.
It is the bottom.
Oh, no.
Not that one.
No, because that would be thinking about it in the context of a specific object here.
Oh, so we don't want that.
Instead, what I'll say is if we look at the surface charges here, we look at the surface currents, I'll be specific. We did write at one point, I think I deleted it here.
Oh, big N? Is that what you meant?
Yeah, but I'm talking here about K. So K would be the surface current, right? On the outside of this thing. And let's see if I have it in my notes here. The earliest piece. Nope. Elsewhere. Okay, well, I'm just gonna write it here. Take a word. Does that make sense? Is that reasonable at all?
I don't know.
Like, guess that?
Yeah.
Yeah, totally guessed it, right? All right, let's have a look here. So here I have this, and I've actually written them both. So I could just take this here for M2, and I could rearrange, no? So I could say something along the lines of M is equal to
that minus H instead.
and what would that be? That would be this piece. Is that possible?
Is it big M like defined over like a volume? Like, so it's like little m over the volume. Okay, so we also have
Big, small. We're not paying close attention here. We're talking about the magnetic polarizability of the material. All right. All you have to do is divide by rho on both sides.
Okay.
Right. So here, what I'm talking about is you have H, you have B. The difference between them is the magnetic polarizability in the material itself. Okay. Does that feel like it's just mathematical mumbo jumbo?
A little
Yeah.
bit.
Okay. All I'm asking you is to keep in mind how these are related.
Okay.
All three of them are related. I start with this. I find it out from the geometry. I have this. I find it out from the geometry. The sheer presence of a diamagnetic material is given to me by the difference. Right? And so I can look at either boundary conditions. I could look at the surface current here. Be like, this surface current is going to generate, by using that current, I can generate a B field that opposes it. That would be the difference. Okay? For diamagnetic material. Okay, useful or not?
So the HS graph is just saying the bigger S is, that's where nothing, there's like no value of H anymore, right?
This would be A. This would be B.
Yeah. Once it reaches it, there's nothing.
Yeah, there's some like object, right?
Yeah.
This little sharp. Okay.
Yeah.
All right. One more example. What do you think?
Speed run.
That's it. All right, let's do it backwards then. Yeah.
Same problems with do with that.
Kind of. I want you to know it inside and out. Now I have to teach you outside and then in.
Willy Wonka? I'm just kidding.
Some people have never said that.
I don't get the reference though.
Because he says things backwards in middle.
Really well, couldn't do that. All right, now we have an infinite cylinder. Okay, it has uniform M. What's B?
Ooh. And we just. Are you writing it? Oh, we're thinking.
Or you're working with your friend, or you're thinking about it with yourself. Yeah.
Got it.
Yeah.
That's what
What's inside and outside?
he wanted what B was.
On B.
Okay.
I think we want A, right?
Yeah, we want A.
You want B? Is that what you're saying?
No.
No. Okay.
On the outside.
But it's like,
Yeah, I would just leave it in terms of.
Well, you want to just ask him?
What's that? Yeah, that's legit what I wrote. Yeah. And then I guess the implication of that is infinite. Mhm. What is
You can ask your friends to think about it. Are you getting it?
No.
This one's nice. Andres, you getting it?
No. For me,
Reed, you getting it?
for inside.
Just put that outside. Okay.
What is
You getting it?
what is the long cylinder made of? Is it stuff?
I just told you that has polarization, magnetic polarization, M
Yeah.
in the upwards direction.
is the M outside or inside?
Physically, it's inside,
Inside.
and it's along the entire length of an infinitely long, whatever.
Long.
So like a cylinder, wire, whatever you want to call it.
Yeah.
And it's in there. The M is pointing up uniformly.
Okay. It might not.
Very good question.
Yeah.
Yeah. So,
Can't we just say like?
Okay, so let's work through some of those thought processes because I hear some things that I like and then I hear some people who are completely lost. Okay, so when you see something like this, what are you thinking to yourself? Other than God, really another one?
Where's the current?
Where is the current? Right? So the first thing you might be asking yourself is, Mateo, you're a liar. You told me that B fields can only be created from currents, and now you don't show me a single current, right? So now you're pissed.
Yeah.
Okay, it's okay. We're gonna get through it together. Yeah.
I wanted to answer like where the current.
Where do you think the current is?
So with this, it has a magnetic polarization uniform upwards. I think the current would be traveling along the side of the wire, kind of like a surface charge.
Oh, so then we have an analogy to surface charge and surface currents. I like analogies. I do, because usually they're helpful. So in general, we had this type of problem. Maybe you solved it where you had a long rod and it was uniformly polarized, right? And from the polarization, you figured out the electric field in both directions. Here, we're going to do something slightly different. So instead of worrying about an external B field creating M, instead of thinking about currents that are going through this object, we're going to say, what does just having a magnetic dipole moment do? Okay. So first we have something like J, the bound current, is del cross M. Do you remember this from the end of last class? Okay. What is that?
I don't know how much spinning there is. Would there be? Is this subject?
Yeah.
Okay. Yeah.
Wouldn't the curl mean PHYS?
oh, for this one specifically. I thought there's more.
Is there a curl?
Yes.
Yeah, I guess if there's a
What is the curl of this vector field?
0.
0. There is no curl in this vector field.
Okay.
Straight.
Because it's straight. Okay, a uniform M has no curl. We need to get these deep inside of our hearts, right? Curl, divergence. We understand what they physically mean. And we're going to drill that into our head along with Ampere's law, right? That's me hitting it into your head with a baseball. Okay?
Just say this with the baseball.
Curl of this field, zilch. Good. All right, what about we're running out of time, but what about this one? So this is KB, and that is I'm not going to let you answer that. Unfortunately, we only have 1 minute. I have to run to a strike meeting because we may be going on strike soon. But that is not the thing that I wanted to end early to talk to you about. So I've been getting the homework back. So far, it's been okay. I think a lot more people need to work harder on understanding what the hell they're doing. It looks like some choices that are being made are not well justified. And if it looks to me like they're not being well justified, then I can't see that you understand it, even if the algebra is perfect, right? So I said at the very beginning, and I'm going to stand by this over and over and over. Algebra is a tool. You need to be able to do the algebra, but you need to be able to know what the hell you're doing. So I'm going to look at this third homework that's coming up. And, one of the things that I got back from the ungrading assessment that we did for fluids is that some people said, well, the lack of like deadlines and tests made it so that I kind of slacked off. So I'm going to look at the results of homework 3. And I think that if that doesn't, like if we don't get the type of results that you would get when you're having strict deadlines, then we're going to have to switch to tests, right? Because otherwise, right, I don't know what I can do. I mean, you cannot slip in this class. And if you're not turning homeworks in on time, or if you're sort of understanding the material, you're going to get absolutely lost. And if you're planning to go to grad school, if you're planning to use your physics degree in any way, shape, or form, this will be one of the classes that you absolutely need to master, right? Okay, people okay with that?
Sure.
And tell anyone who's not here.